So, okay, hello everyone. So I'm exactly feeling like Freddy, super happy to be here, to see so many friends. And maybe contrary to Jan, I also had my birthday a while ago, like 5 years ago, but I was very lucky because Stéphane was there and a few people here, but okay, we had a much smaller event. Okay, so about the talk. So advanced computational imaging, Chassez le naturel, il revient au galop. So for those who are not like French speakers, so if the natural gets driven away, it will come back galloping. Well, okay, I'm not sure if it's the best translation, but it's a famous French saying. So you may wonder, if I give a talk, what's the naturel? Okay, so the naturel, of course, I mean, we're at Stéphane's birthday, so l'ondelette, and then la spline. Okay, so that's could be a definition of the naturel. And maybe now to give some context, you know, with Stéphane. So there's this paper that we have seen many times mentioned, but this is really a classic of all time. And, you know, if you look at it, it was absolutely visionary. So not only is there the wonderful theory of the wavelet transform, but and also the algorithm that, you know, like was mentioned also by Yves Meyer. But then actually Stéphane had the vision of lots of application, because there are lots of application that kept people almost busy for 10 years then, implementing. So there was the idea of doing coding, of analyzing fractal processes, etc. And so you know, I mean, before I would say deep learning, this was maybe the upper bound in terms of citations you could have in mathematics and signal processing. But now, of course, now you have you know, this exponential growth related to machine learning. But now, okay, so Akram told the story about you know, we being not really aware of the paper, and so then actually this, if you go in the same issue of PAMI, so it's exactly the same journal, so you can look here. Okay, so July 1989. So there's a paper by this gentleman Mir. Yeah. Okay, and also Akram was talking about Murray Eden, so he's here. But you would say, you know, at that time, in fact, PDF didn't exist yet, so you see a little not so good quality of the pictures. But even if you go on IEEE, I mean, that's the way they were scanned. And now, if you look here, so you see multi-resolution in the title. And if you look at that, actually, this looks like a neural network. Okay. So in fact, there are filters. There's multi-resolution. You know, even this table looks a little like you know, the description of a neural network. And there's even the spline here. Okay, so you could say maybe that's an ancestor of UNet. And, well, okay, it didn't make it quite the citation. In fact, it's completely unknown, but okay. And anyway, so what's important is to have fun when you do it, okay? Okay, so what the connection now with Stéphane is most of the story, like the beginning, Akram told about. So there was Oleg Tridiak. In fact, he was in Philadelphia, so where you were doing your thesis, and so he got us aware of wavelets a few years later, but it was like I guess 1 year later, and you know, told us, hey, did you see this paper of Mallat? And I must say, even if it was in the same issue, maybe I think I had tried to read it, but maybe I didn't understand too well at the time. But then I was lucky, even there was no internet, no PDF, at least I had the issue. So the day after, I went to read the paper in great details, and with Akram that get us really inspired to do wavelets as well. And then I met Stéphane, I guess 1 year later at a conference. And so we had lots of interaction, and so we became very good friends. You know, so it goes back to 30 years. So many good things have been told about Stéphane, how visionary he is, etc. So let me throw in an anecdote that there are also a few times where Stéphane didn't have such an easy way. Okay, and let me tell you of one. One was, in fact, he had to go through a very tough interview for getting the position at ENS. And I was part of the committee. No, that's a joke. Okay, he had an easy time. But the other thing is, you know, he had, after he created the company, let it wave, and at some point, so he was completely immersed in the company. And then you know, what's amazing, he came back to academia. And so I remember actually meeting with Stéphane when he was just doing the transition back to academia. And actually you told me, yeah, you know, it's a little hard because I'm not sure if I will still be creative. No, if I will be able to catch up, you know, do something, you know, that's valuable scientifically. And then he had this idea to turning to AI or machine learning rather than doing signal processing and you know, wavelets, etc. So that was also like very inspired that you know, that you would just take a new subject and you know, with super success. Okay, so now let's about the talk. So I'll give you a little historical background because here we have lots of people who have been active here. Then I mean, starting from image reconstruction, emergence of deep neural networks, and then you know, some more current stuff. And so the problems I want to talk about is the advanced imaging in the title. So you want to solve inverse problems. So we have seen many in this this symposium. So the problem here being to recover this unknown signal here from the noisy measurement, where you have some model of your imaging device, and this has been discretized. And then the very traditional approach are those variational approaches. And so here you have your data consistency term, here your regularization. Just to make it very simple, like in the 20th century, people would put a 2 norm, and then came, you know, compressed sensing, and we decided, or we were shown that it's better to put a L1 norm with lots of advantages. And so you mentioned Wiener, okay, but we can also mention Tikhonov. In fact, it's equivalent. So the idea of introducing regularization, and then let's setting, because if the problem is ill-posed, setting it like that, like you say, you want to recover within the measurement noise, and you put an energy, you minimize, you put the Lagrange multipliers, you get this cost function, and this you can do closed form because, you know, first we do easy stuff, then you get this nice equation here. Now, okay, this stuff here, you always have the back projection. In fact, also historically, if you look at every modality, the first reconstruction algorithm the people do when they invented a modality, they always did that. And then people come and say, yeah, you can do a little better. So then you put that, and that's the filtered of back projection. Okay, so that's the p equal 2 story. So let's move to the p equal 1. So we're going fast in history. And so the idea here is to add some L1 regularization. And then there's this really fantastic algorithm. This is, I mean, one among many, but the forward-backward splitting, where actually you can solve this problem here, where you may have a non-smooth regularization by first doing like a gradient step on the data term, and then doing a prox on the regularization. And actually, what is this prox is almost the same problem as here, but just it is with the H, which is identity, so it's a denoising problem. So if you have the efficient way to do denoising, then you can just essentially couple the algorithm of the 20th century with a little denoising and iterate, and you are guaranteed it converges, and that's very beautiful. Okay, so this, okay, so it's what I said here. And yeah, of course, you saw very briefly, but Emmanuel and David, the wonderful theory of compressed sensing. But okay, so the relation with Stéphane here, it's now if you want to do that efficiently, you can use wavelets. So for example, if you put like a sparsity constraint in the wavelet domain, now it turns out, I mean, this is a very easy exercise to show that if you do the prox with a L1 constraint in the orthogonal wavelet domain, you have this very simple algorithm, which is, doing Stéphane's algorithm. You go in the wavelet domain, you do Dave's soft thresholding, you come back, and here you are. And then you have this iterative soft thresholding algorithm here, which is just super easy. You do gradient step, you do soft thresholding in the wavelet domain, and Ingrid showed us also that this converges. So this very simple algorithm. But then there were many connections with known stuff also in convex analysis. Okay, so actually we also did some work, some years ago in MRI. And if you compare here the L2 or the L1, it really on real data, it almost systematically gives you better performance if you have less measurement, and also even if you don't have less measurement. So then it actually made it, oops, I'm going too fast. Yes, I have nails of guitar player. Okay. So it was applied to all kinds of modalities with good success, to the point that, the manufacturer of MRI, so they've incorporated compressed sensing sequences so that you can do faster imaging. But then came Jan, deep learning, okay, and it changed things. Then I mean, if you just look at the algorithm, so it's a succession of a linear step, which is the gradient, and then some nonlinear step, which is actually just a soft thresholding. And in fact, then it was actually Jan, so it's an early paper, who just did unrolling of this type of ISTA algorithm. And then the idea was actually to learn, instead of using the filters, that were dictated by let's say the mathematics, let's be bolder and just learn them. And in fact, at that time I had a postdoc in my group, and he really insisted, let's do deep neural network. This should work better for doing image reconstruction. And we were at that time working on compressed sensing. And so there we thought, oh, this is great for doing compressed sensing, because you have the ground truth. It's a reconstructed image using lots of views. And now we will do lousy reconstruction with a few views, train a neural network, how to regress it on the good quality image. And so he did that using UNet. He didn't know my old paper, but okay. Amazingly, I mean, actually this depressed everyone in my lab, okay, because, just very short, okay, here's the ground truth, filtered back projection here, if you downsample by 7. If you do now those 10 years of research of compressed sensing, in fact, this led us to a 5 dB improvement. And then here comes Kyung, and 5 more dBs right away. So this, okay. I mean, we were actually lucky. We wrote it up in a paper. Apparently, some committee of IEEE liked it, so we got an award with that paper. I mean, this works. You know, many other examples is almost kind of systematic. You really get improvement that are absolutely remarkable. But of course, we were not the only one. I mean, everyone had heard Jan, and everyone was doing it at the same time, more or less. So there were many other developments around wavelet. And then it's almost replicated the story of compressed sensing, maybe faster. So they started applying it to every possible modality in sight, publishing in Nature or other high prestige. So now it's too late, okay, guys, sorry, but okay, okay, so that looked really good. Okay, but I mean, now is the but, okay, so I mean, there are also like the weaknesses, because I mean, you need lots of data. Lots of training data. This is really hard to get in the medical world because of privacy issues. Then it's also like computer intensive. So for example, at EPFL now, just have my president here is very much in sustainability. And so this is exactly the reverse. Like if you have more and more powerful computers, that's not so good for our planet. Then they are very hard to tune. Fortunately, we have good students who are good at that, but it's a bit ad hoc, batch normalization. But this is maybe the much more troublesome part. Actually, they lack stability. And that made it actually a big story. So starting with Anders Hansen. So people knew that. I mean, they were observing that it would not always work. I mean, if you feed it data that's a little too different from what it was trained in, they can get completely crazy. And I mean, this was a very troublesome example, because now then they started like doing almost clinical trials. Okay, so this was in Sloan Kettering Hospital in a big database of MRI images of people with tumors. And so they started trying to replicate and applying the algorithm. And so here's so now you know it's good for the compressed sensing guys. Okay, so is someone who has a tumor, here comes out the compressed sensing reconstruction. It looks a little lousy, but the tumor is still there. And here you have the deep learning. Tumor is gone. Yeah. So that got people very nervous, to say the least. Okay, so let's go back to the drawing board. and in some sense, it's not so surprising, okay, because it was like an open loop. Usually in the reconstruction, you have this feedback mechanism. The least would be at least to be consistent with the measurement, but actually that's not enough. Huh? But so now if you go back to this classical algorithm, classical algorithm here. So if you look at the prox, I mean the prox is a denoiser. So the idea is why don't we replace the denoiser by a neural network? And then we have guarantees, but only now if the Lipschitz constant of this denoiser here is smaller or equal to 1. Otherwise, you don't know what's happening. Okay, so if you want to be sort of prudent, it means construct a neural network so that a good denoiser so that your Lipschitz constant is 1. It's not so easy. Okay, so let's now look at the structure of a neural network. So just an easy deep neural network. So you have all those linear layers. The neurons, you have nonlinearities, typically ReLUs. And so what can you play with? Okay, if you want to bound the Lipschitz constant, actually Lipschitz, you can bound it by the product of the Lipschitz constant.
The Lipschitz constant is in what norm?
Here it's in the L2 norm. Okay, so for the filters, it's just you know, the maximum singular value. And for the nonlinearity, actually, we're lucky. ReLU has a Lipschitz constant of 1. And so here, so if the filters are not you can just divide them by the spectral norm. But actually, we found in our investigation, it brings us back to wavelets and frames. We actually found that if you now put a frame constraint there, it's much better, okay? But then actually, you can still play with the nonlinearity, and there we got lots of juice out of the nonlinearity. So let's learn the nonlinearity, okay? And so learning activation or pointwise nonlinearity. And so now this is a scalar guy. So learning a function is ill-posed. So we just put in some regularization, but we have to find one that should not penalize simple stuff like identity or affine function, should be differentiable because we want to apply back projection, and also favor simple piecewise continuous piecewise linear and continuous function, because as Rich told us, splines are very good. Okay, and so what is the natural regularization that emerges? So it's the second order total variation. And you can also easily compute the Lipschitz, so that's in that case you see it's just the actually why do I put the inf here? It's the sup. Okay, sorry. I need the inf for another problem. But okay, so and here's your search space. So it's the search bounded variation functions. Now here's a present for you. It's Stéphane. It's a strange present, but I wanted to take a bottle of wine. I could, it's a little clunky in the. So a present here is a theorem. Wow. Okay, here's the theorem. So let's try to fit some data points. We put we want to design the optimal nonlinearity for Stéphane. So we are going to fit points. We put this regularization on the total variation. But now it's very important. So that's the new part. Okay, we are going to put constraints on the slope, and I will tell you why. So you can put constraints from above, from below, and guess what is the so the theorem, the solution is non-empty, so it's good. We compact, okay, that's good. But, wow, all the extreme points are linear splines. And so there I see Rich being happy, okay? Myself, I wouldn't prove the theorem otherwise, okay? I'm biased. but I'm pretty confident it's correct. And then we even have, so because the solutions are typically not unique, we even have an algorithm to find the sparsest one. And so, for example, here it's actually the Debar algorithm is also, this is one of my former PhD students. So it can really like fit the points. Oops, okay, only 5 minutes. Yeah. Now what are the interesting cases? So if I put the bounds to be 1 and -1, I get Lipschitz. If I put 0 and 1, I get firmly non-expansive. Why is this interesting? Because it's a prox of a convex potential. If I put it 0 and nothing on the top, I get monotone, which is nice because it's a derivative of a convex potential. And if I put it slightly negative here, this will be very interesting. I can construct weakly monotone functions, which actually will be prox or derivatives of weakly convex potential functions. Okay, and then based on this theorem, I can just, this is then a two-liner, get this one, that now if I want to optimize a whole neural network, and I just put this constraint, so, okay, spectral normalization constraint on all the weights, Lipschitz, from, with the constraint, for example, here, then actually the solution of every nonlinearity, so every neuron should be a spline. Of course, you don't know which one because you still have to learn it, so you need an algorithm. In fact, this is just a variation of a paper I did where I didn't have the Lipschitz. Now, the amazing thing with splines, you put all those other Lipschitz-constrained, it's still splines. And this is not trivial, okay, that this happens. Okay, so now what does it mean? So we have a representer theorem, says every neuron should be a spline. It has some knots, we don't know where they are. We just know there are fewer knots than data points, so it's not a very good bound, but those need to be trained. So we also know there's a link with L1, because actually if you look in the formula, there are the weights in front of the ReLU. Actually, the total variation is just the L1 norm of those coefficients, and we can also easily compute the Lipschitz. So then, I mean, the thing was to find a good algorithm. So there we're lucky. Actually, for the good algorithm, you should not use ReLU. You should use B-splines. And the reason being because if you have one data point, if you put B-splines like those triangles, a data point just contributes to 2 points, 2 basis functions. So actually our algorithm is almost as fast as training a ReLU network. Is actually twice the price. You know, so it's super efficient. So we can train all the neurons. And then also what we have in our optimization, we have some projectors on those Lipschitz-constrained subspaces, so that we can impose the constraint of monotonicity or firmly non-expansive, etc. And then, okay, let's apply it, okay? So then the strategy here, we're going to train a denoiser, so we just put like a CNN type architectures, but now all the filters are constrained. Actually, we found after some investigation that it's better to put Parseval filters here, so that then we apply it to MRI. So first, some results for denoising. So here, just as a gold standard, is a non-constrained neural network. Okay, I mean, it's an unfair comparison because if you take a very long ReLU network, you put the Lipschitz 1 constraint, actually it can only reproduce 0. Because it's a sort of upper bound, okay? So, but if you don't put too many layers, so here's your non-constrained ReLU layer networks. If you constrain it, it does much worse. But now with the Parseval frame and the design of the nonlinearity is able to do much better. And then if we apply it to reconstruction, actually, we're able to improve by some dB. And at that point, we were quite happy. But then something else came. I have 2 students working on the problem. They're using different strategies. So the others, so that was the algorithm of Stan. And now is the algorithm of Alexis. He's actually also from Polytechnique. Very, very good, very good student. And there we gain another 1 dB. So let me reveal a little the architecture of Alexis. So actually Alexis' architecture almost looks like compressed sensing, except we are learning the potentials. And we allow them to be not necessarily convex, but weakly convex. And then we have actually here a sort of steepest descent algorithm. And now this is a recurrent neural network, but because it will always do the same thing, and we learn everything. And because of the theorem, now we can say that if we put like a optimality criterion on the nonlinearity for the weakly convex, it's also a linear spline. And so we are using deep equilibrium for training that, so that we're really sure that's the optimal. And now let me show you the results. Actually, the results are pretty amazing. Actually, this was the first sort of variational technique that beats BM3D. Okay, so no, but what I mean, we have been trying for at least 15 years to beat BM3D. This guy beats it. But then if you put it inside the MRI reconstruction, it actually behaves better. And it's almost state of the art. So this Mickey. So I don't know where's Mickey. Yeah. So I think this guy is in your table is one of the good performers. Maybe not as good as the diffusion, but I mean this one is like considered as a state of the art. We're almost there, not quite. Little half dB missing, but yeah, almost there. But now this is the important part, okay? The important part, so people just report so I'm almost there. I've just 2 slides. The people always report the signal to noise ratio, okay? And so here you see TV. This is a convex learned, weakly convex. So we see, we have like, substantial improvement versus TV, and that here's state of the art. He has better signal to noise. But now, those guys, we have all theoretical guarantees, convergent, consistency, stability. Here we have nothing. But now, look at this. The image looks really good. What is this? It hallucinated. And this is really, it is, when I told my students, look at the pictures, okay? So, yeah, we're almost there, and we don't hallucinate. Okay, so what do you choose? Okay, so and this guy you can interpret. So now, okay, now you interpret. It has filters. Now we look at the filters. We're very happy. Okay, un panorama d'ondelet is just not one. There are many. Actually, we need like to put about 80. And the nonlinearity we learn une spline bien dimensionnée. And, Chassez le naturel, il revient au galop. Okay, so that's essentially what I wanted to tell you. Okay, so I will not conclude much more, but at least here we have an architecture that's sort of safe, conforms with what we like, and it's almost state of the art. So, okay, so a few references here, and last thing, cher Stéphane, bon anniversaire, et puis œuvrons ensemble pour promouvoir l'intelligence naturelle.
Question. Thanks, Michael, for very nice talk. So I have a question on. So you are relying on this layer-wise Lipschitz control so that you can
yeah.
stability.
Can you speak up a little bit?
Yes. So I was wondering if you have some thought about how maybe perhaps relaxing a little bit this upper bound and maybe trying to understand interaction between 2 layers. If you could actually improve the Lipschitz control by just looking at how essentially the eigenvectors align across 2 different layers.
Yeah. So actually, it's an excellent question, and that's exactly we were thinking a lot along those lines. And actually, the solution came with the Parseval frame, because the Parseval, it means the filters, they actually align. All eigenvalues are 1. So we don't have a problem. So it actually means, okay, the filters are more constrained, but then actually our bound is pretty sharp. And now what's amazing, so Stan, first student, he started getting really good performance when he put the Parseval, so which were tight frames. So I had like to insist a little as the advisor, because so put old stuff. No. well, and then actually with Alexis, so is even better, like the weakly convex. There we analyzed the WE learned, and it's super close to a tight frame. So there seems to be something magical, like if you put the Lipschitz-constrained, actually the tight frame really helps you, and then you evacuate the problem somehow.
Other questions?
Okay, so there is a theorem which says that whatever is good on the world is a spline. But now, if we go in the spline family, in one dimension, you can get B-spline doing better than linear spline and so on. in high dimension, is linear spline the best of the world?
I mean, so that's a huge part of my ERC grant right now.
Okay.
but we are doing some progress because we had like to come up with a generalization, proper generalization of this TV of the second derivative. So what I can tell you what it is you take the Hessian, the nuclear norm of the Hessian, and then you do the total variation of that. And I mean, I had a conjecture there that actually the extreme point of the unit ball of those guys should be pyramids. And then I went to see Luigi Ambrosio and actually got very interested in the problem. And now they almost proved, you know, that it's almost that, but not quite. But then, because there's a little more, there's a little closure on top of it, but but so those are really the favorite thing. So if we have at least an energy, and this energy actually looks also a little similar to a roughness energy that Rich had proposed, but which is a sort of a discrete version of that. This is you know, using duality theory, etc. So somehow this could be a way somehow to generalize that thing really in higher dimension. And then in my ERC grant, my idea is that if instead of doing let's say just pointwise nonlinearity, actually why do we do higher dimension? But not too high because it becomes, you know, untractable, but maybe 2, you know, 2 to start. And then you can still do neural networks with, you know, 2-dimensional nonlinearity. It can only work better, okay? So, and then actually it's easier to control their Lipschitz-constrained of those guys because, I mean, they can be designed to be just Lipschitz.
Let's thank Michael again.